Okay, well, good evening, everyone. It's 7 o'clock Eastern time, so we'll try to start on time. It's absolutely fantastic seeing so many of you online this evening. I'm seeing from my live numbers about 70 people currently watching this, which is fantastic. Thank you for taking the time to join us, and through the talk tonight and some of the future ones we have planned, I hope we can both keep you entertained and engaged in learning in the coming weeks ahead. For those of you who haven't met me, my name's Jonathan Crass, and I'm a professor in the physics department here at the University of Notre Dame. I'm also the coordinator of the Our Universe Revealed series, the public lecture series from the Department of Physics that you're listening to right now. Over the next few weeks, we're going to be attempting to move all of our planned talks for this semester online. And you can find out more about our schedule, future events, and things like that, either at our website, which is nduniverse.org. You can sign up there for our mailing list. And you can also find out about our events on our Facebook group, which is Our Universe Revealed. So if you enjoy the event tonight and want to hear more about our events in the coming weeks, please go to one of those avenues and you can find out more about what we'll be doing in the coming weeks ahead. For those of you who are familiar with our talks, this evening is going to be a little different. It's going to be about 30 minutes of a lecture style talk, followed by questions. Now, because everything's online, we're not going to obviously be able to take questions as we go very easily. So during the presentation, there's a few ways you can ask questions as you go, and then we'll collate those at the end. If you're watching on YouTube, there is a live chat on the right-hand side of your screen. You can post questions in there and I'll be monitoring as we go. I've also just posted a link to a Google form we'll also be taking for questions. If you're using Zoom, I've also sent you a link there to the Google form. You can also use the question and answer section on the bottom of your Zoom screen. If you hover your cursor over, you can ask questions there. I'll collate them and then we can ask them to Sarah at the end. Obviously, this evening's a first time for everybody for doing this type of thing. So if you have any comments and questions, things like that afterwards, please do drop us an email at universe@nd.edu or via our Facebook group. I'd love to hear from you so we can continue to improve these events as we move forward and do things that you guys would like to see. So without more of ado, that's more of the logistical side of things out of the way. It's my pleasure this evening to introduce Sarah Dietz, who's a graduate student in the physics department here at Notre Dame. Sarah did her undergraduate at New College of Florida in Sarasota before she moved to Notre Dame in 2014. She now works with Professor Tim Beers and Dr. Vinnie Placco on the search and study of some of the oldest stars in the night sky. And that's actually what she's going to be talking to us about this evening. So Sarah, thanks very much for moving to an online format, and over to you.
Thanks for that introduction, Jonathan, and thanks for everything you've done to help facilitate making this talk remote. I'm looking forward to more people being able to potentially view our Universe Revealed series in the future if we continue this online streaming format. And if you have to leave the talk partway through, I believe that this talk should be uploaded in full on the Universe Revealed YouTube channel if you want to check it out later. So like Jonathan said, this is a recurring series of talks at Notre Dame where the theme is sort of science that's accessible to everybody. I've seen a variety of my colleagues do talks that range from topics such as time travel to the future of spaceship building. And hopefully you'll find my topic interesting as well, and that is galactic archaeology. So let's go to... So this was the slide that was used to advertise this talk. And if you saw this, you might have wondered what exactly is galactic archaeology. I've never heard of that before. So I like to joke to people that galactic archaeology is to what I actually do as the Indiana Jones films are to regular archaeology. It's definitely the exciting way to describe what usually consists of a lot of sitting at computers and analyzing data. But I hope to convince you by the end of this talk that we get to participate in some really interesting scientific findings as well. Maybe not exciting enough to make an adventure movie out of, but we'll see. So there's some alternative names to describe what we do. Rather than galactic archaeology, maybe paleontology would be a good analogy. I'm going to make a lot of comparisons between studying ancient stars and studying things like dinosaur fossils. And I recently heard stellar genealogy, which I quite like too, because in a way we're looking at modern day stars like our sun, and we're tracing back their ancestry through the history of the universe. So in essence, what we're trying to do is we're trying to build a time machine to go back and look at the first stars. And there's a variety of ways to do that. And the specific way that I and my research group at Notre Dame study this is by looking at stellar fossils in essence. So just like I said, there's a lot of similarities between this and paleontology. So we have paleontologists that study these huge, ancient, long dead dinosaurs that roamed the earth millions of years ago. They left fossils behind that we can dig up today. And if we study those fossils, we can try to recreate what they looked like with varying success. And there's actually a lot of similarities between this and stellar astronomy. So what we do is we're studying these huge, ancient, long dead stars, and we try to discover what sort of fossils they might have left behind that we can still observe today to try to recreate what those first stars might have looked like and what the early conditions of our universe might have been. So stars obviously don't leave behind skeletons or bones in the same way that dinosaurs and other animals do. So what exactly do I mean when I'm suggesting we study a stellar fossil? So evolution is key here. Just like we can see the modern day descendants of the dinosaurs, creatures like lizards and birds, still on the Earth today, we have stars like our sun, which are in essence grandchildren of the first stars in the universe. So studying the grandchildren and children of those first stars can help us get information about what they might have been like, and we can reconstruct its skeleton, so to speak, from those fossils. So the specific type of stellar fossil that I and my research group study in particular is a kind of star called a carbon-enhanced metal core star, or CEMP star for short. So that's a lot of terminology at once, but I'll try my best to make this fairly straightforward. I'll give you an introduction to what these stars are, what makes them good stellar fossils, and what we can learn from fossil stars like these. So part of that name had metal core as a phrase in it. So what exactly is a metal core star? So on the left here, you can see a classic periodic table of the elements, like you might have seen in your high school chemistry class. And you can see all of the different subcategories it's divided into. On the right is a sort of oversimplified version of what we might call the astronomer's periodic table, where we have hydrogen and helium labeled in the upper left and right corners respectively, and everything else is just labeled with a catch-all term, metals. So in astronomy, metals just refers to anything heavier than hydrogen and helium, the two lightest elements. So to give you an idea why we have this sort of oversimplified view of all of these elements, I'll show you a slightly more complex version of the astronomer's periodic table. So if you look at the key here, it shows you where all of these different elements are created. And you can see, if you notice some of that color coding, that quite a lot of these elements are formed inside stars or from stars' explosions, supernovae, which is a really violent kind of stellar death. In fact, almost everything in this table is made by stars. You have the exception of these human synthesized elements down here in gray. And then these sort of two top sections, the hydrogen and helium, coded in blue to indicate they were created after the Big Bang via the Big Bang fusion. But all of that middle stuff is through various manners created by stars. So that kind of lets you know why we have this oversimplified view where we say, okay, hydrogen and helium, those are the elements present after the Big Bang. Everything else, in essence, made inside of stars. And so that lets you know that the first stars, since they were the first to come after the Big Bang, they would have been formed only from that hydrogen and helium, because of everything else that comes after is created inside of stars, those were the first stars to start that creation process. So the very first stars were different from stars like our sun in that they were made purely of hydrogen and helium, and they started that metal synthesis process. They were also different from modern day stars in a variety of other ways. We don't know exactly what the masses of the first stars were, but they're believed to be anything between 10 times the size of our sun and hundreds of times of the mass of our sun. So the reason they were so large is because the conditions in the early universe were different than the conditions in the universe today. So at the start of the universe, all of that gas that was produced after the Big Bang, that gas full of hydrogen and helium, was very hot and energetic, and it could only start forming stars once it started cooling enough to be able to clump into lower energy pieces that would then condense into stars. So because that gas was so hot and not as cool as it became in subsequent generations, that gas could not cool into small clumps, it cooled into very large clumps, and those created very large stars, larger than the stars you would see today. And because they were so large, they also had very short lifetimes. So you could think of an analogy between a very fuel efficient car versus a sort of gas guzzling vehicle. So in this scenario, a small modern star like our sun would be the Prius, and a large ancient star would be the Hummer. So those large ancient stars, because they were so huge, they burned through their fuel very violently and quickly and died much sooner than stars with a smaller size normally would. And so that's kind of our loss, because since they died so quickly, we can't observe any of them today. And that's why we have to look for these stellar fossils to try to figure out what they might have been like, since we can't observe them directly. So here's a diagram that has a lot going on, but I'll break down some key parts for you. On the left here, you see this concept that I've already introduced in the last few slides, and that's that those first stars would form from the direct byproducts of the Big Bang, so clouds that were made just of hydrogen, helium, and a tiny bit of lithium. And those stars were the first stars to start that metal creation process inside of them. So when they died via, say, a violent explosion, those metals got blasted out into the rest of the universe. And so later, when more stars started to form in that second generation of stars, they were formed from clouds of gas that had not just hydrogen and helium, but also other stuff like carbon, nitrogen, iron, things like that. You could think of it as a kind of stellar inheritance. So each generation of stars can make its own metals, but it also inherits some from the previous generation. So the second, third, fourth, fifth, sixth generation will be even richer in metals than the last. And that's sort of what brings us back to that metal poor terminology and why it's so important. Because in general, if a star is very metal poor, it also means it's very old. There are other ways of estimating a star's age, but because a lot of them require very good data on that star, a sort of easier way to assume that a star is ancient and might be a good candidate fossil is to look at how many metals it has. So here's another way of phrasing what I was talking about in the previous slide, and we sort of get into that stellar genealogy subtopics, since this is sort of a star family tree. So down here on the bottom, we have what we'd call a population 1 star. So this includes stars like our sun that are born today that are already enriched in metals because they're the byproduct of several generations of metal synthesis in stars before them. Up here at the top, you have what's called a population 3 stars. So those would be those very first stars in the universe that were massive and didn't have any metals inside of them, the ones that burned quickly and violently and died a long, long time ago. In the middle, we have what we'd call a population 2 star. So those would be stars that came after the first generation and have some metals, but not as much as the population 1 stars. So this section, the population 2, is where we want to look for stellar fossils. That's our sort of missing link in the evolution of these stars. And you'll notice that in the population 3 category, I tried to represent what I mentioned previously, which is that these stars tended to be much more massive than stars that we see today. But in the population 1 and 2 categories, I showed that they can have a variety of sizes, including fairly small. And I want to stress that one aspect to the studying of stellar fossils in population 2 is that it's specifically the small ones that we're going to observe today, because the larger stars, if they're second generation stars, they're still going to be born a long, long time ago. They're going to be very, very old. So they had to be particularly small and fuel efficient if we want to still uncover those stellar fossils today. So I hope I've adequately explained the metal poor aspect to these carbon enhanced metal poor stars. So let's get into that other half of the name, the carbon enhanced. So here's that astronomer's periodic table I showed you earlier. And you can see that carbon can be formed both in dying low mass stars and in exploding massive stars or supernovae. So scientists who study metal poor stars have noticed that the stars that are particularly metal poor, so probably particularly old and good stellar fossils, seem to have quite a lot of carbon. Stars can make carbon themselves and they can inherit it from previous generations of stars. And these stars in particular seem to have possibly inherited quite a lot of carbon. So if these are potentially second generation stars, that means that that extra carbon inheritance could give you maybe some more information about that first generation of stars that we still don't have as much information about as we would like. And there's a variety of theories as to where this extra carbon comes from. For instance, for a while it was thought that all of these stars might have gotten their extra carbon from a binary companion star. So you may have heard of binary stars before, but just in case you haven't, so a star like our sun, we only have one star in our solar system. It doesn't have any binary partners. But in fact, it's pretty common for stars to be born in binary systems. So that means you have 2 or more stars that are orbiting a shared center of mass together. And depending on the exact conditions of that binary system, like the distance apart, the age of these stars, sometimes mass from one star can be transferred to another star in that binary system. So that's called binary mass transfer. And you can see kind of a nice artist's rendering of what it might look like over here, where you have mass from this star on the right being sucked into this star on the left. Also down here, we have a nice illustration of a binary star you can view for yourself in your backyard. So this pair of stars in the crook of the handle of the Big Dipper, if you have particularly good eyesight, you might even be able to distinguish by eye that it's 2 separate stars, but surely with any sort of basic backyard telescope, you can take a look at it and you can see that this pair, Mizar and Alcor, are a binary pairing. And we're just sort of lucky that in this case we can see them because they have an exceptionally large distance between them. They're about 1 light year apart, I believe. And usually we can't tell that easily if a star is a binary. That's why it was sort of contentious for a while that we didn't know if these CEMP stars got their extra carbon from a binary companion. And it turns out that that binary scenario is true for some stars. So for certain species of CEMP stars, they have a companion star that is old and dying and is creating carbon, and that carbon, along with some other elements on its surface, gets transferred to the metal poor star, and we see it having more carbon than makes sense. But it's not true for all types of CEMP stars. There's definitely some CEMP stellar fossil species that have extra carbon, but don't especially often occur in binary systems, at least not more so than any regular star does. And so one cool consequence of that is that those stellar fossils they must get their carbon enhancement from that very first generation of stars. You may have seen this quote by Carl Sagan before, that we're made of star stuff or we're made of stardust, as paraphrased in some spaces. So you may have already heard this, that the different elements in our bodies were once synthesized by stars. But I think an especially cool result of studying these stellar fossils and these carbon enhanced metal poor stars is that we realize that the carbon in our bodies specifically might come not just from stars, but from the very first stars in the universe, actually. So I mentioned on the previous slide that there's different species of these CEMP fossil stars, just like you have different species of dinosaur fossils that you can uncover across the globe. So we have some CEMP stars that got extra element enhancements from binary stars, like shown up here, as I discussed on the previous slide. And you have some species of CEMP stars that got extra enhancements from very violent and rare astronomical events, like a supernova, which is an explosive death of a star, or a neutron star merger, like the one that was in the news a few years ago. And these are interesting to track because they give us extra information about when, where, and how often these rare stellar events might occur by tracking these distinct type of fossil stars. Another useful thing you can do with fossils is to track the assembly of our own galaxy. So I've made another dinosaur analogy here. On the left, you see a supercontinent made up of some modern day continents. If you remember back to your high school geology, you might remember that all of our continents were once part of one giant supercontinent called Pangaea. And then as the tectonic plates drifted apart and collided with each other, you get the continents that we see today on the Earth. And one of the ways that we can try to piece together the continents that we see today into what they might have looked like millions of years ago is through tracking fossils. So as this diagram shows, for instance, if you see the same types of fossils in the coast of South America and the coast of Africa, you can hypothesize that those two continents might have once been linked millions of years ago when those dinosaurs roamed the Earth. And we can do something similar with the evolution of our galaxy, of the Milky Way. So I'm going to start this little movie for you. This is a simulation of what a galaxy like the Milky Way might have undergone in its formation over the past few billion years. So our galaxy actually has a very complicated creation story. So it's made up of a lot of different galaxies that have collided over the years. We've got some stars that were born here, you could say, and some stars that immigrated here from other galaxies that collided with ours, possibly billions of years ago. And you can imagine that if we have, for instance, as many mergers of galactic satellites as shown in this video, that it would be pretty hard to reconstruct that history and figure out exactly when, where, and how all of these different stars came to be part of our galaxy. And that's sort of what this aspect of galactic archaeology is about, not just about studying the first stars and the condition of the early universe, but also helping reconstruct our own galaxy. So here's another short movie I'm going to show you, and this one shows another galaxy merger, but instead of many galaxy mergers all at once, it specifically shows you one small merger, and it's going to show you what happens when the stars in this red dwarf satellite galaxy merge with this blue host galaxy, somewhat like our own Milky Way. So that smaller galaxy gets torn apart by the blue galaxy, and you can see that the red stars eventually become pretty smoothly interspersed with the blue stars. So that's sort of the puzzle that we're trying to piece together when we use galactic archaeology to study our galaxy. Because we only see this picture, and if we don't have enough information, we wouldn't know that these red stars were ever part of a galaxy separate from the blue stars. So essentially what we're trying to do here is we're trying to take this present day picture and reconstruct what might have happened in the past, possibly billions of years ago. So we're trying to reverse engineer the galaxy in some sense. And that's where we use these kinds of stellar fossils, just like in that supercontinent reconstruction picture I showed you. So for instance, if the stars in this red galaxy are chemically different from the stars in the blue galaxy, maybe they have different kinds of fossils, for instance, if we study this modern day picture, that can help us piece together what might have happened in the past. And here I'm going to show you some of the cool discoveries that we've made with galactic archaeology over the years, using these techniques with these stellar fossils. So here's a nice little diagram showing you the different parts of the Milky Way. If you're not an astronomer, you may not be familiar with it, but you've probably seen some nice artist's rendering that looks like this. So that's our nice spiral galaxy there. And this is a top view. So if you look at it from its side, that circular part is actually pretty narrow. That's the part of the galaxy we call the disk. And that's actually where we live. So you can see in this diagram, we're labeled right here. We live about 8 to 9 kiloparsecs from the center of the galaxy. And you can see that there's a lot of different things going on in our galaxy. It's not a uniform structure. So you've got this disk where you've got a pretty dense population, same with the bulge. And then you've got this sort of more diffuse structure that's called the stellar halo. And that's actually something that I personally research a lot in my work. And one of the cool discoveries that's been made in the last decade or so is that the stellar halo is actually not just one complete object, but there's at least 2 different parts. So the nearby inner halo and the more distant outer halo are actually different enough in their characteristics and their fossil stars that we think that they have different origins from each other. So the outer halo, for instance, is actually rotating in the opposite way that the rest of the galaxy is rotating. And we can find more metal-poor fossil stars in the outer halo than in the inner halo or the disk where we live. So that tells you not just that there might be a different origin story for those different parts of the galaxy, but also that if we want to find even more great candidate fossil stars, where you should be looking. So in this case, that outer halo, since it's so metal poor, we might find even more interesting potential second generation stars there. And there have been even more recent discoveries with the Gaia Space Telescope. So the Gaia spacecraft was launched in 2013, and it's estimated to keep going until about 2022. And the Gaia mission is to get precise motions for around 1 billion stars in our galaxy. And the precision of this information is unprecedented. And because of that, even in the last year or two alone, there's been so many very groundbreaking discoveries being made with data from the Gaia telescope. I've showed a rendering of one such discovery on the right here, and that's the merger of the ancient galaxy Gaia and Enceladus. So scientists believe that about 1 billion years ago, a galaxy that has stellar mass at about 1 billion times our sun's mass merged with our own galaxy and formed most of that inner halo that I mentioned in the previous slide. There's also been some discoveries that suggest other mergers, like a massive galaxy called Sequoia that could have created that counter-rotating outer halo. So as our data becomes better and better, as our telescopes become better and better, we're learning more and more about the history of our galaxy and when these mergers occurred. One thing to look forward in the future of astronomy would be the launch of the James Webb Space Telescope. It's been delayed for a few years, but it may launch in 2021, hopefully. And you can see in this diagram here, it illustrates the scientific capabilities predicted for the James Webb Space Telescope compared with other revolutionary telescopes in the past, like the Hubble telescope that produces a lot of popular images of deep space and supernovae and such that you may have seen on the internet when you read articles about astronomy. And here on the timeline, it shows what you might call a look back time, where over here is our present day. And over here, as we move to the right, we get closer and closer to the beginning of the universe. So this is suggesting that the James Webb Telescope can look into the past up to around maybe 200 million years after the Big Bang. So what exactly does it mean if we say a telescope can look into the past? We've talked about stellar fossils and using those fossils to extrapolate what might have happened in the past, but this is a different kind of galactic archaeology altogether. So you may have heard the term light year before in science class or in science fiction movies. So in short, it's a distance measurement. It's the distance it takes for light to travel in a year, because light has a finite speed. So as this diagram shows, even though the sun is the closest star to us, it still takes about 8 minutes for light from the sun to reach us, because light has a finite speed. And it'll take about 4.5 years for light from the next nearest star system, Alpha Centauri, to reach us as well. So this might give you a little bit of an inkling of what I mean when I say look back in time. So let's say you had a very distant planet that was 100 million light years away, and they had telescope technology that was somehow good enough to observe the surface of the Earth, of our planet, from their location at 100 million light years away. What they would view on the surface of Earth is not us going about our everyday business. They would see dinosaurs roaming the surface of the planet, because the light that's reaching them is light from 100 million years ago. So they're looking into our past because of that great distance between us. And because of that, if we have even more powerful telescopes and we have just the right conditions available, we can look farther and farther into the past, closer and closer to the Big Bang itself. And if we're successful in this venture, that could mean, rather than having to resort to studying stellar fossils like those population 2 stars to figure out what the first stars might have looked like, we could possibly even observe population 3 stars, so that first generation of stars itself, with this telescope, even though those stars died billions of years ago. And I just think that's fascinating, so I wanted to share that. So I hope that this gave you a nice overview of all of the cool things we can do with galactic archaeology. So we're essentially using all these techniques to try to dig up the past and understand how our galaxy formed and what the early universe was like and what that very first generation of stars was like. And even though there's a lot that we still don't know about all of those things, about the formation of our galaxy, about what the first stars were like, I think it's pretty fascinating that we know so much already from our tiny vantage point on our planet, that we can reconstruct what might have happened billions of years ago, shortly after the Big Bang, just from the data that we can observe from Earth alone. So that's my final slide. So I will end my screen share here, and I will transfer back to Jonathan if he has any accumulated questions that you guys have entered into the live chat. Thanks so much for listening.
Awesome, Sarah. Thank you very much. We've had a lot of good chat and things on YouTube. We've got people all over the US watching you right now. As a quick reminder, I've just sent a message out. If you do have any questions, you can ask them on YouTube, the live chat, and the same if you're listening on, if you're watching on Zoom, you can ask them in the Q&A, or also again through that Google. I'm also going to share one thing on here because it's one of my favorite movies that's come out of Gaia. I'm going to send a link out to everybody, but basically there's a huge video that shows all of the motions of those stars from Gaia moving across the sky and how the pattern of the constellations will change in the upcoming billions of years. So I'm just going to share that out. If you're interested, you can follow that link. It will take you out to the ESA website, but it's really cool to kind of see how the constellations and things change and how it maps into your talk. So thank you. I've had a few questions and we'll let some more come in. One of the questions that came out was, what telescopes have you used right now to kind of find these? You talked a lot about, James Webb and the other stuff. Do you use a lot of the Hubble Space Telescope, or do you tend to use other stuff on the ground, or is it kind of a mixture of different things?
So I use a mix of different things. Using a combination of data from different telescopes is often helpful because, for instance, the Gaia Space Telescope provides really precise motions for stars, but doesn't provide as much information, so far at least, about what chemical abundances those stars have. So if I have, say, from a different telescope, information about the metallicity of stars or how much carbon stars have, but I don't have very great motion data for them, I'll combine the data from that telescope with the Gaia data. And I tend to use a variety of different telescopes. So I've used data from the SDSS surveys. So those were the Sloan Digital Sky surveys, from LaMost, that's with a telescope based in China, Gaia Space Telescope, and from just a variety of others.
Okay, awesome. And we've had a couple of questions again about the type of stars and how far the telescopes and things you see. So are the things it's astronomical terms, but are the things reasonably close to us for looking at, or are they kind of a long way away? And kind of the same with the binary stars. And are they kind of close by, or are they much, much further away in astronomical terms?
So the stars that I tend to look at, especially since I tend to study the stellar halo in particular, and if you remember that picture I showed of the Milky Way where it showed where we live in the disk versus the stellar halo, so those stars are very, very far away, and some stars are at possibly the outskirts of the galaxy, you could call it. So I measure the distance in kiloparsecs, so I look at stars between maybe 10 to 50 kiloparsecs away. I don't know off the top of my head how much that is in something like miles or kilometers, so to give people a better sense of how far that is. But I would say I work with some of the most distant stars that you can work with and still stay inside of our own galaxy.
Yeah, awesome. A couple of other things people were asking about the stars in the halo, because aren't they going to be pretty faint? So I think the answer to that is yes. And so you can talk, if you want to talk a little bit about the telescopes that we need and how they're kind of, not something that might fit in your back garden.
So yeah, the stars in the halo are going to be pretty faint, and that does sort of give us some scientific limitations because we're obviously going to get the best data, the easiest, for stars that are A, bright, and B, nearby. So the farther away these stars are, the more difficult it is to get data for them. And that introduces a couple problems. One, it means sometimes we don't have as much information as we'd like to have for distant stars. So we can say, maybe there's some interesting stuff going on in the distant regions of the outer halo, for instance, in a paper that I recently wrote. But we don't have enough information to say something conclusive because we need to keep surveying that area of sky. But one thing that is kind of interesting is, even though those halo stars are very faint, because a number of observational and even theoretical studies, so simulations that make stuff like those movies that I've shown, have shown that even though you actually have more of those fossil stars in the galactic disk, sort of towards the galactic center, there's so many stars in that part of the galaxy that you actually have a better chance of finding a fossil star in the distant galaxy because they have a higher frequency rate there. So even though it's difficult to target the edges of the galaxy, you'll have more luck in finding, sort of without any bias, a nice metal core fossil star than you would if you look in a really crowded part of the galaxy.
Awesome. So I'll do a couple more questions and then we'll wrap up. So there was a question about when you're telling if a star had maybe come from like a satellite galaxy or something else, what were the markers for that? Sort of is it a different chemical content, and how do you tell that? And it was similar kind of thing as, why is carbon special as an element for enrichment? Kind of what's special about that compared to other kind of elements?
So those are both great questions. So for the first one on how you would tell, I guess, if a star had been donated by a galactic merger in the past, you actually use sort of everything you can get. You use a combination of the chemical characteristics and also things like the motion. So even though in that movie that I showed with that smaller red galaxy being torn apart by the bigger blue galaxy, even though it was torn apart very nicely, you can still see that those red stars weren't completely smoothly dispersed through the blue galaxy. They still kind of tended to cluster in specific areas. And if you looked at their motions, you'd probably see that they're moving together in some sense and sort of differently from the rest of the stars. So you use a combination of the motions and the positions of the stars with things like, are these stars chemically different from the other stars around them? Can you remind me of the second question?
It was why was carbon special? What's it special about it for kind of enriching these stars?
So it's not that carbon itself is special, it's that we just happen to find extra carbon here. So theories go back now. So if I reference back that slide where I said, okay, some stars get their extra carbon from binary stars, sure. But some stars don't. We think they inherited it from the first stars. So that means if we're trying to reconstruct not just what those first stars looked like, but those first stars died like, so what kind of supernova happened at the end of their lifetime, we can now constrain and say, okay, those two things, what they looked like and what they died like, have to match up with the fact that they seem to just donate this extra carbon to the next generation. So it's not special in itself, it's just we happen to find it, so we know that that means something about those first stars.
Awesome. Right, so there's one final question, and this is one that as an astronomer, I kind of, so is all of this primarily due to gravity at some level? The whole process, because it's all how stars form and how everything mixes. So is it all really just basically a kind of an effect of gravity in the end of it?
A lot of it is effect of gravity. I mean, if you go back, for instance, when a star forms, actually the stellar lifetime is a fight against gravitational collapse. So all of the nuclear processes going inside of it are actually helping it expand out and prevent all of that mass from collapsing into one spot, which is what ends its life. You have those big clumps of gas that create the massive first stars, and then the less massive second and third generation stars, they collapse due to gravity. You have those mergers in those movies I showed. The reason that they're merging with the Milky Way and getting torn apart is because we have so much mass and we have so much gravity. So yeah, a lot of this does come back to gravity.
So it's the big thing that holds all of astronomy together, right?
I mean, it is one of the fundamental forces.
Exactly. So we'll hold it there, but thanks so much again, Sarah, for a great talk. For those of you who are interested, we're going to actually do another one of these next week. I am going to be actually doing that presentation, so I'll be asking questions to myself, but we're going to be talking a little bit about those telescopes. So I'm sure many of you seen the stunning sort of images that we see coming from the Hubble Space Telescope and telescopes on the ground. My day job, as well as running this series, is actually designing building instruments for those telescopes. So I'm going to take you through a little bit how we design those instruments, how we make decisions so we know we can kind of the things we can study with them. And that's going to be in a talk called Measuring the Heavens. That'll be the same time next week on YouTube and Zoom. That information's all on our website, nduniverse.org. We're also going to obviously post the recording of this talk this evening, so you can go back and watch it again and share it with people. But for now, I just want to say thank you again to Sarah. I hope you've all enjoyed it, and hopefully see you all again next week. Thank you all for joining us online.
Thanks so much, Jonathan.
Bye-bye, everybody.